Lyon, computer engineer. I'm joined today with Evan Magno and Daniel Fine, two electrical engineers. Over the last 2 semesters, we've worked together on a 3-phase motor controller with our technical directors, Dr. David Durfee, Ben Ritchie, and Denise Andriozzi. And all together, we are Team Bay Computer Associates. Today, I'll be talking to you about our project motivation, the best outcome of our project, the firmware and hardware accomplishments that we've made over the last semester, and if we've met that best outcome after all of our work. So our project has seen a couple of different implementations over its life cycle. At one point, it was a controller for a motorized or electrically assisted wheelchair, and as a controller for a motorized bicycle. We'd like to expand upon the possible implementations of our controller, say for larger scale devices such as an X-ray machine or any other large scale medical device. With this motivation in mind to expand the range of products, we have come up with the following tasks to achieve our best outcome. We'd like to produce a higher current output as well as implement a better system for current sensing. This way we can move those large scale devices. We'd like to design a new board layout in order to take up less space with our controller. And we'd also like to develop a position control algorithm, integrate that algorithm into our firmware using fixed point notation. So as far as our firmware accomplishments over the last semester, we have developed that position control algorithm in MATLAB as a proof of concept, as well as a simulation of the algorithm in C using floating point numbers as opposed to fixed point. To get to position control, there was a couple of different ways we could have gone about this. After talking to Ben and Ritchie as to what we would like to do, we came up with what we consider a simple solution, simple because of one design constraint in particular. That would be constant acceleration and deceleration values. This allows us to do some simple stopping distance equations to allow us to calculate and determine when we want to start slowing down and approach our target. Here you can see a diagram of that proof of concept in MATLAB that I had there. For the future of this firmware, unfortunately, we did not get a fully functional implementation of fixed point notation. It just drops too much accuracy at this point, and because of this, it was not integrated into the firmware.
So this semester, my main goals, mostly I worked on implementing a new current sensing technique. I also worked on schematic capture and layout. We'll get to that later. So our project uses low side current sensing as opposed to high side current sensing. So we're sensing the current after load before ground. And we're using, the old original board used a single differential amplifier connected across the sensing resistor for each phase and also for the bus phase, which measures the total current in all 3 phases. So the new design I came up with has 2 differential amplifiers per phase and also for the bus phase. One is for the less than 20 amp range, which gives us higher resolution and still smaller currents. The other one is for the full 200 amp output range. So we have 2 different ranges, higher resolution and smaller currents. I was also able to update the overcurrent comparators. It's another level of protection for the circuit board. This takes the output of the bus phase differential amplifier and compares it to known voltage values using comparators and sends that to DSP for another level of protection. This is a very simplified schematic of my new design. You can see 2 amplifiers, 2 sensing resistors. So the top one's connected across both resistors. That's our smaller, high resolution range. And that's connected across 2 resistors, lets us use less of the gain. And then this is our full 200 amp range. So the previous op amps for the project were actually not fast enough. The gain bandwidth product was too slow. They're not giving us the correct results. So I actually went and found a brand new op amp, the TI-TLB 9062 with 10 megahertz of bandwidth. And it gave us great simulation results. It was fast enough. Did exactly what we wanted to do. And also, since power is I squared R, with 200 amps, that's a lot of power. So we need to choose a very small sensing resistor. So we went with the 200 microohm, 10 watt sensing resistor that can handle the output current. And this is a picture of the simulation I did. Hopefully you can see it. The blue curve is the 200 amp output sine wave of any one of the phases. And the green curve is the output of the differential amplifier that's getting sent to the DSP. So it basically follows the current waveform exactly, which is what we want. You can see it's offset by about 1.65 volts. That's so we only have to use one power supply per op amp. We can just ground the negative supply. And you can see the kind of the peaks are at 0.3 volts and 2.9 volts. So those are kind of our thresholds.
Hello everyone. I'm going to be going through some of our schematic and layout accomplishments that we achieved this semester. Our schematic capture was completed in DX Designer, and we did our layout in PADS Mentor Graphics. So as for the schematic, one of the main revisions we did was to update all the power supplies. We have 4 different power supplies, and we had to update them all because of our increased input voltage, which was 12 to 60 volts. So our 4 power supplies were a main feature of our new design. In addition, Evan just talked about his current sensing. When we were implementing that into our schematic, we were faced with the challenge of having only 4 available inputs on our DSP, while Evan's design had 8 signals to monitor. So this quad 2-to-1 multiplexer will select the current that's being sensed on, or the signal being sensed on each phase of the motor, and send that to the DSP for monitoring. Another task of ours was to go through the previous design and remove any features that are now obsolete, because our new motor controller was wanted to be more of a generic motor controller, so some of the features in the old design were no longer needed. This includes some buzzers and alarms, certain power supplies, among other things. Now moving into our layout, our PCB was a 4-layer board with a circuit component side and a ground and power plane in the middle. Our accomplishments for the layout included power supplies, MOSFET stage, current sensing circuitry, and the DSP placement. These were all our new designs that we had implemented throughout the year. Now as for the best outcome and future of the project, because our project isn't at market readiness right now, we can't say we met our best outcome, but our work, our technical accomplishments over the past year covered a majority of the work needed for this project, and we've left it in a good place for BCA to take and bring it to the market in the near future. So some of those remaining tasks include a few more layout tasks that need to be completed and a full review of the layout. The position control algorithm needs some more debugging and integration of that algorithm into the firmware, as Brandon discussed, and also the board fabrication needs to be completed in the future. We'd like to thank everyone for coming out today. We'd like to give a special thank you to our technical directors, Dr. Dave Durfee, Ben Rich, and Denise Andriozzi, for all their help and guidance all year. We couldn't have done any of this without them. And of course, like to thank Professor Sunak for this great opportunity. I'd like to thank our fellow capstone designers as well. Thank you very much.